Okay, I'll manage.
Okay, cool, thank you.
Okay. Hello, my name is Rolf Häfner. I'm from Sonicona. We're a company that develops the software tool for passive seismic aftershock monitoring for the OSI section. So we're not only doing the development, we're also doing the training of the inspectors. And so I noticed that the method that we apply in nanoseismic monitoring is regarded as quite exotic, even when you look at seismologists. So I think it would be interesting for this wider audience to have a look how it works. And I will just walk you through the location of one single event. We start usually when we are doing seismic monitoring in an academic environment or in a commercial environment. We do a lot of preparation, a lot of planning, and set up a large seismic network. But here at the OSI, we start with very few stations, and we have to start with basically zero information. So what you see here is what our analysts in the OSI tents will see after they installed and brought back data from the first 3 stations. 3 is regarded as the absolute minimum that you can, seismic network that you can use, but we can do better. This is data from monitoring of geothermal borehole. So there were some injections, and what we see here is an event cloud. You see these triangular blue plots are the signatures of small seismic cracks. If I had a laser pointer, I could show you the very smallest ones. While dark ones are obvious, you always have this triangular shape that you can use to identify seismic signals. Let's select one of the larger ones. So to explain, every row here is one station, and every block of rows, it's 3 minutes of data. So what you see is approximately, I think, 45 minutes of data. So you can screen the data quite quickly. Let's select one event. It's marked here in red. You can see the seismograms. It looks like a typical small local seismogram. And what the analyst now does is he starts the tool Hyperline. This software is designed to facilitate an interactive event location process. We have in the upper left an overview of all the seismograms, and on the lower left, a detailed view of the seismograms. The same with the maps. We have on top an overview and a detailed view on the lower right. Then in the middle, we have a depth section and a few panels that will be used for additional information. So this is what we see. We have our event. First, of course, we apply some filtering to get a nice, consistent view. We see one station here is located far to the south. It's the station Balst here on the map. So we focus first on the early arrivals near the PSM stations SNS1 and SNS2. Formerly, they were called SNS. Today, they are called PSM, but it doesn't matter. It's just a name. Each of those stations is composed of 4 stations in close vicinity of about 100 meters. This has a few advantages. For example, we can start with a single station and just interpret this one. Maybe we only have, for the first aftershock, only a single station. And by installing 4 instruments at this location, we can utilize we have to go to this site anyways, so we can set up a little bit more to get more information, because in an OSI it's quite difficult to reach all the positions where we plan to set up stations in this inspection area. What we here see are the traces of these 4 array elements that you can see here on the zoomed in map. Let's zoom in on the P onset. We see here we have the first, the second, and the third trace look very similar. So we select the first significant feature, and we already get an estimate for a slowness vector in the panel here right in the middle. Of course, we have a problem with the second trace here. But as soon as we place the first three picks for this correlation, you see the stack of those traces on the, the fifth line. We see an array beam on our maps, which is our constraint that we introduced to the solution. And we see a back projection of the correlation on the seismograms. Of course, we can increase the scaling of the second trace, and in fact, it's just a scaling problem. Maybe we have bad metadata, or we have some bad digitizer set up. But when we increase the amplitude, it looks similar. We can also pick the first significant feature here. We see the overlap. It matches quite well. And now for each combination of three traces, we get one slowness estimate. And so we can, by manual jackknifing, select the most probable solution, and we see our array beam is corrected a little bit. What more information can we get out of this single station? Of course, we have the P onset. We apply it, but the P onset alone doesn't include any more information that we can use directly. So now we pick S, the S wave onset, and now from the S minus P difference, we get a S minus P circle on the map, which is the constraint due to the travel time difference of the different phases. And now, together with the array beam, we can have a first estimate of a probable event location. So, while this is not robust in any traditional way, now we know where we have to extend our network, most probably, where we can expect more events if this is in fact related to the triggering event. Of course, we can pick S and P on our second station, SNS1 in this case, and now we see the difference in P-wave travel times introduces a hyperbola-like structure. It's not exactly an hyperbola because we already have a layered velocity model. We see a second S minus P circle, and then we can visually compare if these constraints match. Also, if you have two stations and we have only S minus P circles, we usually have two solutions. So the array beam helps us selecting the correct one. So as we move our estimate of the true event location, we see here in yellow, back projected, the theoretical arrival times on the seismogram. So we can check those for plausibility. Here you also notice the third instrument, far to the south. It's very far away. We are not certain about our velocity model yet, so I didn't include this at this point. What do we see here? Okay. Now when you look at the depth section, I changed the event depth, and you see how the constraints move with changing depth deeper and deeper. Now, when we go really deep, this is below, below 4 kilometers. We see now that we get realistic arrival times that match to the third station. And if we go even deeper, we in fact get a solution if we pick there. This is this circular-looking hyperboloid section that is introduced here. But I removed this pick for my final interpretation because at this point we really can't be sure about the velocity model, and we need, if we are spanning larger distances, we need more information about the structure of the lower layers. So let's stay at our two stations. Let's play a little bit around with the event depth. And if we can't get any more information, now we notice we had a large spread in the slowness estimates in the array processing. This may be an indication of an event that is very close, where a planar wave hasn't formed yet, and we would have to use a circular wave approach, or a spherical wave approach. So when we are very close to a station, of course, we can use the small array itself as a small network and start picking P on those outer instruments. And in fact, we get of course, a lot more constraints displayed on our map. We can see here, this is, okay, yeah. This is where I stopped this process. We can't really at this point determine the depth exactly. We have to look at more events, more data coming in, better models. So now we check our result. When you look at the map, this is in the direct vicinity of the borehole. Of course, we see through the constraints there's a lot of variation where it could be. So the location constraint is not as good as this moment, but this is the best that we can get with those two stations. And you really see which constraint. At the time when you do your pick, you introduce the constraint and you can clearly see how each constraint relates to its individual pick. When we're doing magnitude estimation, we do the same thing. We have our epicenter selected, our hypocenter selected, in fact. We also have the depth. And now we use the Wood-Anderson simulation of the horizontal traces to estimate local magnitude. For each amplitude, we check the S-wave amplitude, and out of amplitude and direction, we get in the center bottom, we get this amplitude over distance diagram, where we can estimate magnitude. We do this for the other two traces. As soon as we pick a magnitude, the probable amplitude is back projected on these seismogram simulations. And of course, we can include even the further station, because for magnitude estimation, we don't rely on the velocity model. So we can include this without problem, and it fits really well. You see here the amplitude value at the 30 kilometer mark. And so we have a nice consistent result where we exactly know where each information goes in and how where we can, even with very few stations and very little data, can get a good estimate of how precise our final result is. Now, this is a lot of work, and we were thinking how we can make it easier for the inspection team. In this case, we have a lot of similar events. So today one would say, oh yes, let's train an AI to do it, but that's difficult in the inspection area. So we rely on classical image recognition, pattern recognition algorithms with a twist. We have these spectrograms that we use for event detection. And you see here in the second block, we have the noise of a traveling car overlaid with this event. It's in the second row. And visually, we can clearly see how this traveling car and this seismic event differ. But for an image recognition algorithm, this is in fact quite difficult. That's why we introduced the second step. We not only use the signal pattern, this triangular dispersion pattern in the spectrogram, we also apply the current noise conditions and calculate how this pattern would look under these noise conditions before we do the comparison. Of course, there are a lot of points. This sounds complicated and computationally difficult. But it's in fact quite easy, because we can set amplitude thresholds and say if the energy doesn't, if there's no energy contrast to this local noise, we can skip the calculation and proceed to the next time step. So it's actually quite quick. Sadly, I can't show you any quantitative results yet. We're still in the testing phase. And of course, we always try to include this in our visual and interactive software, so this takes always a little bit of time. I hope I can tell more in 2 years. So let's conclude. Nanoseismic monitoring for passive seismic monitoring in an OSI context. What do? We visualize each user input and each constraint that results from that. When we are picking our final event estimate, we back project this information. So we always try to visualize every step in these calculations so that nothing is hidden in a black box. I think this is especially important in an OSI context where we really have to trust our data. The trust in the data is the foundation of the whole operation. And so if you introduce any black boxes in the middle of this process, there is always a lack of trust or a lack of understanding in what happens at this precise step. And so you can, in your final report, you can display all these constraints, and the audience can really see how you got to this result. Also, this is very good to train people that from adjacent fields, because as you see, everything is visualized. So you don't have to give them all the equations and familiarize them with those. They can really play around. What happens if I select the wrong wiggle? How does this influence my constraints? How sensitive is this thing to changes in the velocity model, to changes in event depth? And you can really start to learn how the solution is formed. So if you are interested, you can try it out yourselves. We have a demo version online. There are 3 data sets included, one extremely local, the one I showed, and some regional data sets. You can try the full functionality of the software with this demo, but you just have to use our data sets. If you buy the full version, of course, you can use any data you want. Thank you.
Any questions?
I don't think they hear you say again.
Okay.
Any questions for Rolf? We do. Andre? No, sorry. 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 Rolf, don't worry, there will be a question. Hold on, stay there. We have 6 minutes left of the session. Please stay there, Rolf. Okay, thank you very much for your presentation. We do have some questions submitted online, so I'd like to ask Joseph and Cornell to come forward to answer some questions which have come on. Cornell, come forward as well, if you don't mind. And in the meantime, the rest of you can think of some other questions to ask the 3 and Go Jiling as well. So first of all, Joseph, is there a normal status quo methodology in comparison to the FISP methodology is the question.
So we are not aware about any other kind of methodology similar to this. When we started in 2015-16, dealing with resonance seismometry, there was nothing. The resonance seismometry in OSI is really defined very vaguely, and yeah, this somehow fits to the description of resonance seismometry. Now we have 2 methods. Another one is that Rolf presented in his poster. Of course, from a physical point of view, finding cavity, identifying the cavities, there is a lot of methods. But if we are looking through the eyes of OSI and through the resonance seismometry techniques, we don't know any about other techniques.
Thank you. Cornell, I'll read it out and I'm going to add something I'll get in the end, okay? What is the threshold change expected from this experiment? How can this be significantly detectable in an OSI context? And perhaps what would be the prerequisites for it to be used in an OSI context would be my addition. So I'll read it out again. What is the threshold to change expected from this experiment? How can this be significantly detectable in an on-site context, on-site inspection context? So, and what are the prerequisites that would make it valuable, perhaps? Yeah.
Okay, excellent question. I would say that at least 3 to 5% of changes would be desirable to make it useful, detectable. Otherwise, if the anomaly which we are looking for is too small, it will be really tricky to detect. But starting from the conclusion of the research conducted back in the 1990s, that they were able to use an airborne imaging camera system, multispectral camera system, and were able to detect stress as a result of the underground chemical explosion of 1 kiloton. I assume that we have the reasonable ground to believe that it can have practical use in the OSI context. The tricky part is to detect the stress, which is specifically related to the underground explosion-generated ground motion. However, vegetation stress is always something to look for because it will be always an interesting spot to check out if we realize something, whether at the satellite imagery scale or later on during the airborne operations.
Okay, thank you, Cornel. We have 2 minutes left on the session. Thank you. Any further questions? Nalin.
To Cornel.
To Cornel.
I think the stress distribution is governed by local geology. So in your model, you consider it as an isotropic sort of a distribution, or you are going to add in future the geological near surface variations also?
I'm not sure I understood the essence of your question. Can you please try to rephrase it?
Because the stress is distributed not in isotropic manner.
Yes.
It has geological control.
It is just a mechanical stress at this point.
Okay, you are taking an isotropic sort of a model. I mean, it is equally distributed.
Yes.
Okay, thank you.
And an oscillation way, a vibration.
So I'd like, time is coming to a close for this session, so I'd like you to thank all 4 speakers. And let's thank all 4 speakers first. Thank you. In summary, I think the spectrum of topics covered in this session, not just in this session, but also in the in the poster session on yesterday and on Monday, encapsulates the range of techniques and methods during an on-site inspection and illustrates how complex an on-site inspection would be, especially when you think that we are talking about 40 inspectors at any one time doing all of these different things. So I'd like to encourage anybody with ideas to approach us in the on-site inspection division. If they have ideas that they would like to develop further, things that we could further investigate, I'd encourage them to come forward and approach myself or my colleagues in the on-site inspection division with those ideas. So for now, I'd like to thank everybody and have a pleasant evening in Vienna. Thank you.